Thanks, and I want to thank the organizers for giving me the chance to talk about our newest result from the yttrium monoxide experiment from Junye's group. And now we kind of like switch a bit gear with directly laser-cooled molecules. And we all know kind of like why we want to access the ultra-cold regime of of the molecules. It's kind of like for the big applications or platforms for quantum information, quantum simulation, and precision experiments. They all can really benefit when we have like additional control and be able like to go to the ultra cold regime. And like for some of the platforms it's necessary, and for some it's only beneficial. And first I want to introduce kind of like our system. It's yttrium monoxide. We produce it by laser ablation of a ceramic yttrium oxide target in a buffer gas cell, which produces like a cold beam where the rotational and vibrational state are like cooled to the lowest state. And then we employ like a chirped laser cooling to decelerate the molecules from around 120 meters per second down to 10 meters per second. And we utilize there a broad transition between a doublet sigma plus and a doublet pi 1/2 state, which provides us fast scattering. And we can decelerate it down to around 10 meters per second, which is in the capture range of our DC dual frequency magneto-optical trap, where we can load usually 10 to the 5 or a bit more molecules with a temperature of around 2 millikelvin. And of course, this is not sufficient for like doing really or like accessing the ultra-cold regime. So we employ like subdoppler mechanisms. And yttrium monoxide is again a little bit special under the diatomic molecules. It has a special ground state structure. So the oxide has no nuclear spin, and the only nuclear spin is the yttrium. And we have like a really strong thermic contact interaction arising from our valence electron and the yttrium magnetic moment. This gives rise to a quantum number G, which is the total spin quantum number, and we have two manifolds, a spin less, the G equals 0, and a spin 1, G equals 1 manifold, which are well separated by around 750 or 80 megahertz. And we have a really robust way now to use like a subdoppler cooling using like a Sisyphus type of polarization gradient cooling, a gray molasses cooling, which provide or is super robust under like a large magnetic field or a range of magnetic fields, where we like at zero magnetic field we reach like temperatures of around 2 microkelvin, and at magnetic fields up to 25 Gauss we still have like a temperature of 20 microkelvin. And now with this we can like always like initialize a super cold molecular cloud, but we cannot further compress it. And we got inspired by the Doyle group, who kind of like developed the mean of a conveyor belt Bloody tuned MOT, or like a compressed Bloody tuned MOT, where we now add an additional tone, laser tone with opposite helicity, which provides a moving lattice, which kind of like really sucks in the molecule into the center of the magneto-optical trap, and we can compress the molecules really fast within 40 milliseconds, down to a size of around 60 microns, and the temperature in this compressed MOT is in the order of like 20 microkelvin. That's why we can reach such a small cloud size. And then we can afterwards freeze it out again with just with the GMC, or the gray molasses cooling pulse, and we can load this cloud to a optical dipole trap efficiently and study two-body collisions. But I don't want to talk here about the collisions work we had recently. I want to talk how can we kind of like further or try to go further in cooling down the molecules, because the molecules are precious, and if you can already initialize the molecule with a lower temperature, we always gain at the end after evaporative cooling. And so yttrium monoxide is again like a little bit special. We have like a low-lying delta state which lies below the first excited pi state. And this is like a metastable state. So with a lifetime of around 23 microseconds, which was measured previously. And this is in principle like an ideal candidate for narrowline laser cooling, where we have like a narrowline transition to it. And we could think to do, for example, resolved sideband cooling in a magic wavelength trap. But we didn't have the conditions for a magic wavelength trap. So we just went further, like we can do as well, like just do ordinary Doppler cooling, because now that the recall limit, or like the Doppler limit, is below the recall limit, and we should be able to go towards like 400 nanokelvin. So the idea is simple. Can we just find like a closed cycling transition between our electronic ground state and the excited metastable state? And this is not the case, because the upper state minimal J quantum number is 3/2. So we cannot enforce anymore like a P1 transition, which will provide us a closed cycling. So we need to kind of like relax the condition of cycling between only one rotational state to two rotational state. So we have a small leakage to the n=3 rotational state. The lifetime of the metastable delta state arises from a small mixing with the pi3/2 state. And as well, this induces the size of this lambda doublet splitting, which is kind of like, as a first estimate, one can say it's a ratio between the lifetimes times the Q or millican Q parameter in the pi3/2, and one would arise in the order of like in the order of like 10 kilohertz, splitting between two opposite parity states in our state. And we did like some high resolution spectroscopy to narrowing in the lambda doublet splitting to below 7 kilohertz. So we know they're kind of like really degenerate, and like a stray electric field of some millivolts per centimeter is sufficient to polarize the system or the upper state. So I don't talk here at 10 kilovolts to polarize the system. I talk here about millivolts per to polarize the system. So this causes some issue with scattering photon on the polarized molecules, because the parity is usually not anymore conserved in the upper state. So we have again like decay to additional rotational state. And this doesn't look anymore so attractive to try laser cooling on 4 rotational states. So we need to find a way to narrow down and kind of like decay to one specific parity state in the ground state. And we found a way to apply, so when we apply electric field up over our molecules, we can polarize the system accidentally. And we can resolve spectroscopically field-sensitive state and a field-insensitive state in the center of the manifold. The field-sensitive states, they have like a first-order Stark interactions, and they are therefore a parity mixed state. And the center state, the MF=0 state, has no first-order Stark interaction, and is therefore like or remains a pure parity state. And therefore, if we use when we can just address this single field insensitive state for doing laser cooling on it, we can preserve again like the parity conservation in a E1 transition. And so the idea is now kind of like straightforward. We initialize our molecules in a single quantum state in the n=1 state, in the sigma, in the electronic ground state. We do this by optically pumping away the G0 manifold and the F=1 and 2 in the G1 manifold into this state here. And then we connect this state with our narrowline transition. And when we scan over the resonance, we can measure the temperature change of our ensemble. And when we are like 150 kilohertz retituned, we have kind of like a temperature of 10 microkelvin, and we see a clear temperature reduction by approaching the resonance. And on the blue detuned side, we see a strong increase in temperature. But with this scheme, we see directly we have like 10 microkelvin temperature here, and I told you before we can like initialize it kind of like in the 2 microkelvin region. And the temperature increase arises from this broad repump lasers, which are off-resonantly scattering always, and so will increase or give a rise like, to additional heating, and this is unwanted. So we need to get rid of any broad laser, and when we just address or use 2 lasers now to address the delta we have state from the G0 manifold and the other one, we can kind of like limit our decay, or like we can close the cycling to 80%. So we have around 4 photons to scatter on the delta state before it goes to a dark state or to an unaddressed state. And with this, we could resolve again like a temperature decrease of around 600 nanokelvin. And on the other hand, like a temperature increase of around 600 nanokelvin. This is approximately like 50% efficiency in cooling. And now it's the question, like, can we increase the photon number budget from 4 to, let's say, 40 or 100, which should be sufficient to go either to the motional ground state of a deep lattice or to the recall limit. And the answer is kind of like when we implement additional laser to, like 1 additional laser to the n=3 state, we can double the photon numbers to around 8. And if we include the first vibrational state, we should reach in of a bit more than 80 photons till we go dark. And so in principle, with 4 lasers, we should be able like to implement or have enough photon cycling to cool the molecules down to the recall limit, and as well, again, enough photons to repopulate the F=0 state efficiently. And with that, I want to conclude. My time is up. And I want to thank my lab mates, Mangshay, Cameron, and Logan, and Junier and you for your attention. Thanks.
Okay, thank you very much for this nice talk. Questions?
Hi, thank you for the nice talk. In the one of the earlier slides, you showed the level scheme for laser slowing. I was wondering if there was a specific reason why you don't directly repump the NS0, but use microwaves, while you do directly repump the NS2, if I understand correctly.
The issue here why we need to address like the other parity state, the n=0, arises from the delta state. So we have like a 2 photon path decay, where like every 2000 photon, it will decay to another parity state. And you cannot kind of like get rid of that. So you need to kind of like, the n=2, we can optically pump down to the n=0, and the n=0 we need to mix in with microwaves. Otherwise, you cannot change again the parity. And like, but this only reduces the scattering rate marginally, so we don't really like lose anything there.
Okay. In the meantime, can I ask a quick question? What are the typical numbers and densities for your molecules?
So like, we can load in the order of like 10 to the 5 molecules, a bit more, into the MOT, into the dual frequency MOT. Then we have kind of like 50% of those remaining inside the after the compression in the subdoppler MOT. So we have in the order of like 50,000 molecules in this subdoppler cooled MOT at 40 micron. And then we load it usually into the dipole trap, where we have like 40 to 50% again, like loading efficiency. So we have like a phase-based density of a bit less than 10 to the 5, A-5. That's currently our regime. But we, as you might have figured out, we have here like a vibrational repump addressing the same J number here. We will replace this to go or connect to the B state. And with that, we can increase the scattering rate drastically. And we should be able like to double or triple the molecular number with this, just because we can address a larger fraction of our Boltzmann distribution for slowing. So we have some plans to really boost the molecular numbers, and shielding is on the way. So that's work in progress.
Okay. This, Lawrence.
In addition to controlling the branching ratios, are there any particular situations where the small lambda doublet splitting can be especially advantageous?
Yeah, like The delta 3 half has a bit of short lifetime of 23 microseconds, but the delta 5 half state has like a lifetime of, it's calculated of 300 milliseconds. So it should be enough kind of like to do their dipolar physics with electric fields of some millivolts per centimeter. So it reduced the complexity of studying dipolar physics drastically. That's in principle like the long-term access for. It's probably not that hard. So we know roughly the transition. We would do like a kind of like a adiabatic rapid passage transfer to it. So we did not, yeah, we thought on direct excitation.
Okay. Any urgent other question? Then we thank you again for the nice talk.